Hello, my name is Larry Lapides. I'm with Imperas. I'm going to talk today about advanced RISC-V processor verification. The agenda today is to start with an introduction to Imperas, talk about why people use this new RISC-V instruction set architecture, the challenges of RISC-V processor design verification, how Imperas is stepping up to the challenge, what some of the key technologies are, and then we'll provide a summary. So let's start with an introduction to Imperas. The Imperas founding team has a background in electronic design automation tools and also with FPGA and processor IP companies. The founding vision was that embedded software development is ready to embrace simulation. And as in EDA, specialized tools and methodologies are required. The tools should be developed top-down, starting from these requirements. Today's focus at Imperas is on RISC-V. It's on RISC-V software simulation, just as with the founding vision, but also on design verification. And the interesting thing here is that with the founding team coming from co-design automation, the inventors of System Verilog, and as with myself from Vericity, we all have a background in design verification. And so DV is sort of a back to the future experience for many of us in the founding team. Imperas started looking at RISC-V in 2016, before RISC-V International was founded. It was a little bit academic and fragmented at the time, but very quickly started to converge. And Imperas joined the foundation right at the beginning. We started building models, started working with other partners in the RISC-V community, and very quickly started working with customers. And we've continued up to this point. We're very active in the RISC-V community. Imperas is probably the most active pure ecosystem member. We don't build RISC-V processor IP at all. We're just providing tools. And we've been there since the start. We have a long list of customers and partners on the customer or user side. These include NVIDIA Networking or Mellanox. NSI Texi is a Denso subsidiary, NXP, Silicon Labs, Nagravision, and down the list. But maybe most interesting are these last two. One is that there are numerous universities around the world, and tens of universities around the world that are using Imperas tools for RISC-V. And the second is that with this free instruction set simulator that we provide, and those RISC-V OVP Sim Plus, we have more than 100 organizations that are using this free instruction set simulator, either as a reference model for DV or for initial software development. We also have a good list of partners, including the major organizations in the RISC-V community, working with the test generation companies, Google and Valtrix, the processor IP vendors, including the FPGA companies, and in particular, also working with Intel, who has recently announced their RISC-V Pathfinder IDE. So why are companies choosing to use RISC-V? The RISC-V history is that it began in 2010 at the University of California, Berkeley. The RISC-V instruction set architecture is provided under open source licenses. The instruction set was designed to be usable for practical computing applications. So this wasn't just an academic exercise. This was designed to be used in industry. And the interesting thing here is that the RISC-V specification allows for users to add custom features, instructions, or CSRs. And it's this freedom and not the free. This is why RISC-V usage is growing so fast. What the freedom does is to enable domain-specific processing. So RISC-V is growing in market segments where x86 and ARM architectures are not dominant. So this could be small microcontrollers for SoC management, replacing proprietary cores, uh, vertical market segments such as IoT and AI and machine learning, horizontal markets such as security. What RISC-V provides is the freedom to develop differentiated domain-specific processors. So companies can use this to build products that are specifically suited to the differentiation that they want to show to customers. The RISC-V users include both traditional semiconductor companies as well as embedded systems companies now developing their own SoCs. So what are some of the processor design verification challenges for RISC-V? Challenges in RISC-V processor DV include feature selection and the design choices. So in RISC-V, you have all this flexibility to choose which instruction extensions you're going to use, and also worrying about custom instructions. All of these choices have an impact on verification. And so designers, developers need to trade off the features they're going to implement in the RISC-V processor and the impact on verification, the cost on verification that these features are going to incur. The current SoC cost, 50% of the current SoC cost is for hardware DV when the CPUs are brought in as proven IP and there's no verification required. Developing your own CPU adds incremental schedule and resource and quality challenges. Also, processor DV is a new experience for many teams. Teams have done SoC and SoC subsystem DV, but not processor DV, and that's different. Existing methodologies also have the same bias, this focus on SoC and SoC subsystems, and do not completely address the processor DV challenge. And as of 2021, up until Imperas in December of last year, no commercial products were available to support DV of processors. So how are we stepping up to the challenge? Let's start by talking about collaboration. So Imperas is collaborating with this unique blend of open source, nonprofit, and industry partners. For example, working with Google and Chips Alliance on RISC-V DV, a random instruction stream generator. Working with the Open Hardware Group on Core vVerif, the verification environment for RISC-V processors, which is based on UVM. And also working on RVVI, an open standard interface and API for RISC-V processor verification, which we're working on with Open Hardware Group and also a number of industrial users. So collaboration is a key piece of stepping up to the DV challenge. A second piece is standardization. Standardization is good for both IP users and IP vendors. For users, it supports best practices, supports reuse and portability, supports getting up and running faster with the IP. For the vendors, there's less configurability, which usually means better quality, and then also makes it easier to do customer support. UVM is a good example of standardization in the DV community. In RISC-V, what we've done is to develop RVVI, the RISC-V verification interface. And this has been made available through GitHub. It's an open source project. This work has evolved over the last 2 or more years, actually with Imperas and Micro, NSI Tech's Open Hardware Group, Silicon Labs, and a few others working on this. The idea is to standardize communication between the test bench and the RISC-V verification IP. That verification IP includes both the reference model and additional verification IP that I'll talk about in a couple of minutes. There are 2 pieces to this. One is the RVVI VLG piece, signal level interface to RISC-V verification IP. And the second is the RVVI API, a function level interface to the verification IP. The RVVI VLG is that signal level interface. It's effectively a system Verilog interface that helps go from the DUT, the RTL, through this tracer or monitor module that all processor IP has. They're the signals out going into this RVVI VLG, and then being communicated to the verification IP. And this includes functions to handle asynchronous events such as interrupts. And again, this is available on this GitHub repository. The RVVI API is a set of standard functions that the RISC-V processor verification IPs need to implement. So you can see this is doing step and compare. This is GPR compare, PC compare, CSR compare, on down the list here, as well as getting information from the RTL. So again, this supporting a step and compare methodology. There are both C and System Verilog versions available. Again, available through the GitHub repository. The third piece of stepping up to the challenge is methodology. So methodology is best practices designed to address a known problem. It's built on experience, actually on both successes and failures. And Imperas is defining the RISC-V processor DV methodology in collaboration with our customers and ecosystem partners. And the result has been an asynchronous step and compare methodology for RISC-V processor DV. So what does this methodology actually mean, this asynchronous step and compare? So it starts with stimulus. So this can be directed and constrained random tests. It can also be a random instruction stream generator. The next piece is the reference model. This needs to be a high quality, validated, instruction accurate processor model that is configurable to match processor customizations, both in terms of using the standard extensions as well as any customization, custom instructions, custom CSRs that are included. Needs to be able to run the same software as the DUT, so the same tests, the same ELF files. Needs to be able to respond to asynchronous events. Needs to be able to do comparison. So the comparison is the next step. The DUT, the reference model, run in lockstep. The internal state is completely compared at each significant event. Typically, this is going to be on instruction retirement. Errors get reported immediately so that you can quit the simulation and not waste any more simulation cycles. And this supports multi-hart processors and out-of-order and multi-issue pipelines, as well as handling those asynchronous events like interrupts. And the last piece is functional coverage of instructions and registers, of sequences and scenarios, of interest and the asynchronous events. So these are the main pieces of this step and compare environment. So what does this look like in practice? Well, the initial implementation of this was on the open hardware CV32E40P and the initial core vverif environment. And you can see here the random instruction stream generator based on the Google RISC-V DV, the tests going into both the DUT and the reference model, the Imperas reference model here wrapped in system Verilog using DPI. There are various agents here, a scoreboard for comparison, some assertions that are available here. This was successful. CV32E40P, well qualified core that's been used, put in silicon. So great, this worked. But actually, it took a lot of effort. So how to improve on this? That gets us to the fourth piece of stepping up to the challenge, verification IP. Verification IP enables users to hit the ground running, to benefit from the knowledge and experience of others, helps adherence to standards such as RVVI, supports best practices, saves time and resources, provides high quality verification environment, makes customer support easier. Users do not have to be RISC-V experts to verify a custom RISC-V processor. So here's the Imperas RISC-V verification IP. It's this Imperas DV product. It supports the RVVI standard, supports the asynchronous step and compare, supports random instruction streams, supports asynchronous events. It manages the synchronization and performs all comparison and checking. And users implement this tracer piece here, which interfaces to the RVVI. We see the first RVVI VLG interface here, and then the API interface here. There are these system Verilog modules that are part of the Imperas DV product. These are part of the verification IP. And then we also see over here these pieces built in C. First, the RISC-V reference model, and then verification IP for configuring the model, for doing the synchronization, for doing the compare, pass-fail determination. And also there's a piece for instruction coverage here. This is a very simple C-based coverage. But actually now using this VLG to cov module here, we have implemented functional coverage as part of the Imperas DV. So two additional pieces here to talk about. One is test suites. So there are currently over 50 free test suites available, including this whole alphabet soup here of RISC-V extensions. Just a note, the vector suite is only one vector engine configuration. And then there are also commercially available test suites. A full vector test suite that supports any legal vector configuration. And then also a physical memory protection, a PMP test suite that supports any PMP configuration. And then last, that functional coverage library availability. These are system Verilog cover groups for the different RISC-V extensions currently available for RV32, RV64, IMC. These are open source and extendable, so users can add on their own functional coverage capabilities, and it uses that RVVI trace data coming out. There's also, as I mentioned, that instruction coverage, that simple instruction coverage available for the full RISC-V specification. So what are those key technologies the reference models, and the verification IP. Let's go into those in a bit more detail here. So model requirements. First of all, for the RISC-V model, you want to build something that works not just for DV, but also for software development. You want the software developers using the same model that you're using. The hardware and platform software should look the same. So you want to be able to model the ISA, including all versions of the ratified spec and the stable unratified extensions. You want to easily update and configure the model for the next project. Needs to be user extendable for the custom instructions and registers. You need to be able to model the actual processor IP from different vendors. Needs well-defined test process, including coverage metrics. Interface to other simulators, System Verilog, System C, the Imperas virtual platform simulators. Interface to software debug tools, GDB and Imperas multiprocessor debugger. Interface to software analysis tools. Interface to architecture exploration tools. Most RISC-V instruction set simulators can meet one or two of these requirements. The Imperas models and simulators were built to satisfy these requirements and matured through usage on non-RISC-V ISAs over the last 12 plus years. So just looking at what we've done in terms of the reference model. So there's a base reference model. This is built in C. There's also the Imperas simulator. So there are APIs for model building. The APIs are supported by the simulator. There's a configuration file that has more than 250 parameters for configuring the RISC-V models. That's all within the RISC-V specification. So we provide this specification envelope model. So this can be used for compliance, for verification, for test development. It supports all the different RISC-V extensions and different versions of these extensions. The source is included under the business-friendly Apache 2.0 open source license. Yes, there are a number of users for this. It's used as a RISC-V golden reference model. What about custom instructions? Well, the model is extendable. And the idea is that these custom instructions get put into an extension library. So the base model isn't touched. So those hundreds of users that are using the RISC-V OVP Sim Plus, that free ISS, are also using this, as well as the paying customers. So this means well over 100 users are beating on this base model. And so any customization, any extensions that you're building go in this separate extension library. We provide templates to add new instructions, code fragments. There's a user guide. There's actually a video tutorial for this. So this is an architecture for the model to provide for easy extension, easy maintenance of the RISC-V models. Certainly, we have a library of fast processor models. For RISC-V, we have these generic or envelope models supporting the full specification. We have models of processor IP vendors, and of course, users can build their own custom models. Models are built using a test-driven development methodology. Quality is key here, and when we build models, we're using a test-driven development methodology. So tests are built at the same time as the features are added. We use a continuous integration test flow, and there are well in excess of 15,000 directed tests for the models and the simulator. So every time code is checked in, we're running these 15 to 20,000 tests. And then for the models of the processor IP vendors, there is additional testing by these processor IP vendors to validate the models. Part of that Imperas DV product is also debug capability. The Imperas multiprocessor debugger is an Eclipse-based debug tool. You can debug using source line or instruction level. Uh, you can see new custom instructions and any new additional state registers that you've added in that extension library. And you can break at the first mismatch, and then debug the software and the RTL concurrently. So I know most of the people watching this probably used verification IP before, but let me provide a final word on verification IP and the benefits. It accelerates your development schedule. It frees up resources to work on the domain-specific tasks and not on the verification infrastructure. Provides access to a best-in-class methodology, constrained random, coverage-driven, asynchronous step and compare methodology with debug at the point of failure. Provides access to verification standards, RVVI, which enables portability and reuse. Provides access to a high-quality reference model developed by processor experts, tested by our partners, tested every day by over 100 users. There's also documentation, training, ongoing support for the verification IP. So this is where we are right now. What's next? So in all these areas, improvements can be made. Stimulus, there can be a better method of coordinating the asynchronous events within the program flow. Also, we're working on extending RVPI to add a virtual peripheral interface to provide more verification capabilities, building in more scenarios. Quality of the verification environment is important. So adding in quantitative measurement of the verification quality using fault injection and mutation testing. Functional coverage, so building on those initial functional coverage libraries. And of course, user feedback is important. So to summarize here, RISC-V processor developers need to do comprehensive verification of the RTL implementation. The processor DB methodology has been evolved by Imperas together with our customers and partners. Open standards like RVPI are essential to enabling efficient methodologies and advancing the RISC-V ecosystem. Asynchronous step and compare is the most comprehensive, most efficient RISC-V DB methodology. And verification IP for RISC-V DB equals best practices, open standards, quality reference model. Thank you. Any questions?